In this video, we're going to take a look at the relationship between vapor pressure and temperature. Let's take a look at some experimental data. This is a plot of pressure versus temperature. The pressure in particular is the vapor pressure of water at various temperatures. And the first thing you recognize is that vapor pressure is dependent on the temperature. That is, as the temperature changes, the equilibrium vapor pressure for the liquid changes. You can see here at 760 torr, the temperature is 100 degrees. That's considered the normal boiling temperature for water. And what we know is that above, this is called the vapor pressure line. This line is the vapor pressure line. And above the line, the liquid is more stable, and below the line, the gas is more stable. That makes sense. At the higher pressures and lower temperatures, you would expect, liquid water to be more stable, and at lower pressures and higher temperatures, the gas to be more stable. And when we say more stable, what we mean is that the free energy is actually lower for the liquid under these conditions, and these conditions down here where we have the lower pressure and higher temperature, the free energy of the gas is lower. Now along the line, the free energy is the same between the gas and the liquid. That's why along this line we say it's an equilibrium condition, because the rate of the gas returning to the liquid and the liquid returning to the gas is the same, and it's an equilibrium condition all along this line. Let's look at another plot. In this plot of vapor pressure versus temperature, this is the water equilibrium line here repeated. And what you see here are two other substances, pentane and tetrachloromethane, right here. And you can see that the boiling point is higher, the normal boiling point is higher for water than for the other liquids because it has higher IMFs. And so if you think about, when we say that the gas is more stable down here for the, and then the liquids would be more stable above the lines in each one of these cases. If you think about what we mean by that, the free energy is equal to the enthalpy minus the temperature times the entropy. And so at lower temperatures, the enthalpy is dominating because the enthalpy is all about the intermolecular forces, and when the liquid particles can be close to each other, you're going to lower the enthalpy. Whereas at the higher temperatures, it's all about the entropy dominating. And so at the higher temperatures, that's why we see the entropy factor, which increases with the gas, whereas the intermolecular forces increases with the liquid. So we can see why the gas is more stable at higher temperatures, whereas the liquid we would expect to be more stable at lower temperatures because of those two different factors. Clearly, the relationship between the vapor pressure and the temperature is an exponential function. And so we can derive from the thermodynamic first principles an equation relating the vapor pressure at one temperature and the temperature at one, and the temperature and the vapor pressure at a different temperature. We can do this because, as it turns out, the gas is obviously very dependent on the pressure. And so the change in the free energy between the liquid and the gas is equal to the standard change in free energy for the vaporization plus this term RT natural log of P. And so this is where we get our our exponential dependence. And through some thermodynamic derivations and looking at equations at two different temperatures, we can derive this particular Clausius-Clapeyron equation, which is very useful in estimating vapor pressures at different temperatures. If you know the vapor pressure at one temperature, you can estimate the vapor pressure at another temperature based on this formula. P1 is the vapor pressure of the substance at temperature 1, and P2 is the vapor pressure at temperature 2. Delta H, of course, is the change in enthalpy of vaporization for that particular substance, and R is the gas constant, and we would want to use energy units there.